Thanks for coming back again. If you're a subscriber of this channel, and if you are new here, do well by clicking on the subscribe button and also turn on the notification bell to let you know when we drop our new videos. So we want to talk about a significant equation in physics and optics, to be precise. That is the lens-maker equation that is very useful for every lens manufacturer out there. So let me first of all write the form in which the equation is, then we'll talk about what is the usefulness and maybe the derivation. Okay, so the lens-maker equation is equation that is written in form of 1 over f equals to the refractive index minus 1 multiplied by 1 over r1 minus 1 over r2. Good. This is the lens-maker equation, and this R1 and R2 represents the radius of curvature of the two glasses used or combined to form the lens. It's an equation that enables all lens manufacturers to produce a lens of a given focal length. So if I want to produce a lens of a given focal length, probably 15, so I have to make sure that I use my lens-maker equation to know how my construction will look like. So we are going to look at how the equation is being derived and the usefulness. However, there are two limitations to this equation. One of it is that the lens have to be a thin lens. It has to be a thin lens, and the two glass materials that should be used that are used should be the same material. It shouldn't be different material. So if you are getting a glass material, make sure you are using the same glass material for your lens combination. So that is what the limitations are. So but now let's consider what the lenses, the two glasses of the lenses that are combined to form the lens itself. So we have a glass, curved glasses. So when we say curved glasses, we might be looking at mirrors, but curved glasses, a curved glass is not coated on any side, so which means both sides are uncoated. So for instance, if you have to represent that with diagram, a curved glass is this. So but a curved mirror is this. One side of the mirror will be coated, so that makes it a mirror. So this one is just a glass. So I can combine two glasses to form a lens, like the convex lens we used to know is two glasses combined together to form it. So we have something like this with a pole separating the two glasses. So that's a glass. So now when we come about radius of curvature, we are familiar with radius of curvature when it talks about mirror. When you draw a curve, if you try to complete it, I think you form a circle after completing. So the radius of this circle is what we term as radius of curvature, because after halving or cutting off one part of the circle, we eventually get our half glass. So definitely the half glass will still have the radius of curvature. So we call that the radius of curvature. So if we are to derive this equation now, we are deriving it from two equations. The two equations represent one for the refraction that takes place on the first glass, and the other one from the refraction that takes place on the second glass, so that are combined to form a mirror, a lens. So we have this. So let's say an object is placed here, and image is formed somewhere here. So we have zone this and this. So image is formed somewhere here. So we believe that this is the incident ray from the object. Are we getting it now? And this is the image line of view. So in a nutshell, we are talking about n, the refractive index of this first part of the glass to be n1, and the refractive index here to be n2. So the radius of curvature of the first glass tube is r1, while the second glass tube is r2. So the equation that represents the refraction that takes place on the first glass is n2 over v1 minus n1 over u. And this will be equals to n1 minus n2 over r2. So this is the equation 1 that represents the refraction on the first part of the glass. Then on the second side of the glass, the equation that represents the refraction that takes place there is going to be n1 over v minus n2 over v1 equals n2 minus n1 over r1. So this is the second equation, which represents the refraction on the second part of the lens. And mind you, v is the object distance while u is the image distance. So you are seeing v1 here. They are from the same glass material. So if we separate the glass and we allow object to be viewed separately, we are going to have the same image distance, so which represent as v1, which is different from the image form when both are combined, which will represent as v. Are we getting that now? I'm going to correct something here. So this is supposed to be n1 minus n2, while this is n2 minus n1. So now, how do we derive the lens maker equation? Since we are joining these two glasses together, then we have to add these two equations. So by adding these two equations, we get our lens maker equation. So let's go ahead to do that. So this is the first equation, this is the second one, so let's add it. So in order to add it, this, I would love to add it with this, so that is n2 over v1, that will be minus plus minus this, that will now give us n2 over v1. We know that will be 0. Now let's take this and this together. So I'll be having minus n1 over u with plus n1 over v1. Okay, so this should be v rather. This should be v, not v1. So then we have to add the other side too. So all will be equals to this, that is n2 minus n1 over r2 minus n1 minus n2 over r1. As this, we go with this, then we'll be left with the common factor here is minus n1, and I'll be having 1. Sorry, I've made mention that this will be v, not v1. So I'll be having 1 over u plus 1 over v. Good. So in a nutshell, I have to move here and add up. So in order to add them, I can factorize it. So from here now, I think if I multiply this minus with everything there, I'll be having n2 minus n1 over r2 with minus, sorry, that will be positive, n2 minus n1 over r1. So this is what I have here. Then the common factor is n2 minus n1, n2 minus n1. Mind you, there is a mistake here. Once I factorize and bring down minus n1 here, this is supposed to be negative, okay? So then I'll be having minus n1 into 1 over u minus 1 over v, okay? Then that will give me n2 minus n1 into 1 over r1 plus 1 over r2. Mind you, addition is commutative, so this is allowed. Okay, let me just continue my work here. I love managing birds. So from here now, I will just have to divide both sides by minus n1. So if I do that, I will have 1 over u minus 1 over v equals to n2 minus n2 over n1. Then I will have minus n1 over minus n1. Okay, so this still remain 1 over r1 plus 1 over r2. In a nutshell, I'll be having this to be 1 over u minus 1 over v. Okay, so this is one frame. 1 over u minus 1 over v, all equals to, this will give us negative refractive index. Meanwhile, that is the refractive index of the two glasses together. Then this will give us plus 1 into what? Into 1 over r1 plus 1 over r2. So in a nutshell, how do I simplify this? Whenever you now place an object at infinity, that is when the object distance is at infinity. Okay, let me drive the camera closer so you can see what I'm trying to talk about. So if the object distance is at infinity, then u will be equals to, v will be equals to f. So in that wise, I can change this to infinity, 1 over infinity, we can neglect that value to be 0 because it's actually very small. So since the value of 1 over infinity is small, here we just become negative 1 over f equals to, then if I factorize this out, I will have minus refractive index, okay, minus refractive index minus 1 into 1 over r1 plus 1 over r2. So the minus here, we have to cancel the 1 here, then we have derived our length meter equation, 1 over f equals to this minus 1 into 1 over r1 plus 1 over r2. So this is therefore our length maker equation, and that is how to derive it. The equation is very useful for the lens manufacturers out there, and I've given the limitations that comes around with the equation, which means the lens have to be thin and the glasses have to be the same material. Thanks for watching. Please come more and more times to get more wonderful videos and share to those who need them. Thank you.